Hello, everyone. Come on in. Sorry it took a little extra time for me to log in, but we should go ahead and get started. But I wanted to go ahead and begin with asking you guys if you have any questions, and also reminding you that you do have impending online test and a couple homework assignment, one or two that are due this weekend. So make sure you knock those out. If you want to check the dates on the MyLab and Mastering website for the dates on the homeworks. And remember, we've only covered chapters 1, 2, 3, 4, 5, 6, and 7. So those dates are the only ones that are definitely correct. Once I start covering chapter 8, then that date will be correct. As far as the test date goes, there's an online test due, and you get multiple attempts like you always do, all that good stuff. That date is spelled out right on the practice test as well as the online tests that are on the main page of Canvas in the online tests module and in the practice test module. So, anybody have any questions before we get started? Okay. Well, last time I started off showing you a dot product, and then I showed you how to work it and what that was used for. I even gave you the big picture that we use dot products often in vector calculus as well as in physics and mathematics to find the component of a force that happens to be parallel to another force, or the component of a vector. If you want to find the component of a vector parallel to another vector, then you can use a dot product. And I even gave you a little derivation of a projection operator that you can use. That's something you often would learn about, say, in linear algebra or something like that. But it just gave you some more feel for what the dot product does. There's also a cross product. We'll learn about that when we get to rotation and torque. And the cross product, unlike the dot product is also called a scalar product. So it just spits out a scalar, a number. It takes two vectors, A and B, or A and A, for instance, and you get A dot A comes out as a scalar. So they call that a scalar product, but they also call it a dot product, and it also is essentially the same thing as what we call an inner product. Then there's a cross product, and that one takes two vectors, A or A and B, for instance, and it spits out a vector. But interestingly, that can be used to find the component of a vector, let's say A, that is perpendicular to B. So not what A is and not what A parallel to B is, but specifically what part of A is perpendicular to B, and we could use the cross product for that one. And like I said, the neat thing is that one spits out a vector. In fact, that ultimately becomes something we generalize to the wedge product that we can use to calculate areas and even volumes. If we combine both the dot product and the cross product, you can even compute volumes in three-dimensional space or areas in two-dimensional space. So that's some of the stuff we use. Uh, it still looks like no one's asking any questions, so I will go ahead and move on. You can go ahead and type me your first and last name in the chat section, so I'll have you as here as roll. And what I'm going to start off with is an example, and I'm going to share my screen to do that because it's kind of a pain in the butt to actually put it in this iPad sheet. So what I'm going to do is share my screen here with you, and you can see the first example. It says, example one, determine the work required of a hiker that is wearing a 17.5 kilogram backpack as he smoothly walks up a hill of height h equals 12.5 meters at a constant speed. The hill is shaped like a ramp whose inclined surface makes an angle theta with the vertical. Notice I said that's with the vertical. That's different than what we normally do. B, determine the work done by gravity on the backpack. So that's the problem that we're asked to work on in this first example. I'm going to open up my iPad. I've now got it open. I'm not sharing it with you yet. I'm just writing down the information. So I have example one. Again, I'm just recording this on the uh, iPad sheet. And what I have is a mass of 17.5 kilograms. What I have is a height equal to 12.5 meters, and an angle theta with the vertical. So what I'm going to do for this is I'm going to draw the actual incline, and so that you'll have some understanding of what I mean about theta with respect to the vertical. So the height I'll draw that on this figure as well. And uh, what you'll see is a person carrying a backpack. And basically, what we're looking at far as the backpack goes is we have a weight mg, and I'm still writing down the numbers. I know I'm not sharing with you yet, but that's okay. I'm doing it because I got to write down all the numbers first. I'm going to go ahead and multiply 17.5 times 9.8. That's 171.5 newtons. And we also have the force by the backpacker, which is F sub BP, that points up. And this is the mg is the weight, or excuse me, is the force by gravity. So that's Fg. And the person's going to walk up the incline. All right, now I've gotten all that information written down. Now I'm going to stop sharing and start sharing my iPad screen. I apologize for it having to be this way, but there is another way. It's just not, it's still not trivial. So, all right, so any second, the iPad screen should be coming up. Any little second now. All right, so this is the drawing I have. You can see my little backpacker walking up, and technically the backpacker is walking up that whole slope. We don't know what that distance is. And in fact, all we really know is that the backpacker is walking up that height, and that height h is 12.5 meters. And notice the angle theta I said was measured with respect to the vertical. So that's me showing what I mean by measured with respect to the vertical, like that. Okay. So let's get to working on it. What we know is work is equal to the integral of F dot dl. In this case, we are actually dealing with a constant force. And in fact, I'm going to imagine a very distinct scenario. So in this scenario, I'm going to assume that that this backpacker is walking up the incline at such a slow rate that he really doesn't speed up at all. He just sort of maintains a constant speed, and he's pushing up on the backpack with the minimum force he can to actually cause it to move upward. Of course, he's also walking a little bit forward with the minimum force that he can to walk forward. Uh, all of that's going into the work, and we're going to use that to calculate. So, since he's not actually speeding up, we can say that the summation of the forces in the y direction is equal to mass times acceleration in the y direction. But as I was telling you, he's walking so slowly and he's putting the minimal amount of force on the backpack so that it's just barely enough force to keep it from falling to the ground, and just enough force to cause it to move upward a little bit. If you were to have, say, a mosquito fly under it and hit it by accident, that would give it just a little bit more so it can move up. And then you wait a little while longer and the same thing happens. So it's really trying to go that slow. When we do it that slowly, that means it's really not accelerating at all. And the acceleration in the y direction would be zero. And then what we get is that the force that the backpacker applies minus 171.5 newtons, which is the force that gravity provides, all that has to equal zero. So we know that the magnitude of the force the backpacker applies is 171.5 newtons, and that point 0.5 is really not a sig fig because we only started with 3 sig figs, so we can only have 3 sig figs at best, since what we did was just multiplication. So in this case, it is a constant force, so the work ends up becoming just F dot, let's say, delta L, where delta L technically should be that distance right there. Let me clean this up just a tad bit. Okay, so this distance, whoa, Nelly. So this distance right here is delta L, and you could even treat that vector as the vector delta L. Uh, you can see it's basically the hypotenuse of the right triangle I've drawn in here. So we're going to go about doing that, and we're just using sort of our dot product, which we figured out last time. So for part A, they want to know the work done by the backpacker. So that's the work done by W sub BP. And that's going to be equal to 171.5 newtons. That's the force. And in order for us to dot product it, we would multiply the magnitude of that force times the magnitude of the delta L, and then times the cosine of the angle between the two vectors. So I'm going to write cosine, but realize that it's not necessarily the number I'm looking for, because remember the dot product is defined such that if this is vector A and this is vector B, once they're tail to tail, then the angle theta is the one that separates them at their tail. So that's actually what the A dot B is equal to A B cosine theta is about. If we look at our diagram, we see a vector that's like delta L vector there. And what we see for the force that the backpacker applies is that backpacker is really just applying a force upward. So this is the force of the backpacker. Now, if you notice, the angle theta that we had was the angle that the incline, which is this part right here, it's the angle that the incline makes with the vertical. So the angle that the incline makes with the vertical happens to be this angle right here, which if you look back at the diagram, you can realize that that angle is theta. Now, because this line, this dashed line is vertical, and this vector is also vertical, these two lines are parallel, and that makes this angle and this angle alternate interior angles. So we can now say this angle is the same because alternate, and here's the wording in case you need to look that up, interior angles. So when you have a bisector, a straight line crossing two parallel lines, then alternate interior angles are equal. So that's what I've just shown you, is that the angles are alternate interior, so therefore the cosine is the cosine of theta. So I can now put in cosine theta here. Now, what does that mean? If I look at this diagram, I see that cosine theta is equal to adjacent over hypotenuse. Well, the adjacent is actually h. So h over delta L is what cosine theta is. So that becomes 171.5 newtons times delta L, but cosine theta is h over delta L. So the delta L's actually cancel one another out, and luckily we happen to know what the H is. So we get 171.5 newtons again times the H, which is 12.5 meters. So when I multiply this, I get 171.5 times 12.5, and that gives me 2,143.75. And the units are Newton meters, but as I told you, the Newton meter is defined to be a joule, a Joule. Just for your own knowledge, the joule is about as much energy as it takes to lift a good, nice, succulent, red, delicious apple. Like if you go, maybe now, maybe the end of next month, we'll start getting really good apples like in Harris Teeter and Food Line and stuff like that. And if you grab one of those good sized red delicious apples, that'll usually be roughly the right weight to do this calculation. But if you actually take that apple and lift it from ground height onto a bar height, or actually onto uh, a dinner table height, then that would be 1 joule of energy. So a joule of energy is about as much energy as it takes to lift a red delicious apple from the ground to the top of a table. Now, if you think about that and you realize that 1 watt is 1 joule per second, then you realize like a 100-watt light bulb is basically the equivalent of lifting 100 red delicious apples up to from the height of the ground to the height of a kitchen table 100 times in 1 second. So 100 apples lifted up every second is about how much energy you're wasting per second when you're running a 100-watt light bulb. So that gives you an idea what a watt is. That also gives you an idea what a actual joule is. Now we only had three sig figs, so technically the 3, the 7, and the 5 are not significant figures. So you really should write this answer as 2.14 times 10 to the third joules. And that is the work done by the backpacker. Anybody have any questions on that one? Now, in the other part, like I said, they wanted us to calculate the work done by gravity. Now, in that case, you actually have the gravity force acting downwards. So this is the force by gravity, and that force, of course, is 171.5 newtons. So if we want to calculate the work done by gravity, this is how we do that. Work done by gravity would equal the gravitational force, which is Fg, times the delta L times the cosine of the angle between them. Now you see that the angle between them is actually this big guy. So I'm going to call that phi and write that as phi like that. Okay. Now, this might not work out as much, but there happens to be an identity that relates the cosine of uh, of an angle to 180 minus that angle, and that's really what we're looking at. Phi, we can rewrite this as Fg delta L cosine of 180 minus theta. So then you could look up the sum of angles or the difference of angles formula and calculate that. But what you would find out, of course, is that it's basically acts like the cosine of sort of the smaller part of that angle. But really what it is basically a negative sign. So in place of what we had before for delta L times cosine theta, we're now going to have negative delta L times cosine of theta like we had before. So in this case, I can write it as 171.5 newtons times delta L. And remember, let's look up the I'll look up the actual trig identity for cosine of difference. Cosine of the difference of two angles. So the identity that we're using here is cosine of A minus B is equal to cosine A cosine B minus sine A sine B, or excuse me, plus sine A sine B. Okay. So what we're going to do is we're going to say that in place of this cosine of 180 minus theta, I'm going to go ahead and write it as cosine 180 times cosine theta plus the sine of 180 times the sine of theta. Okay. Well, if you look at our graphs, for instance, for cosine, it looks like that. This is 180, and therefore we get a negative 1. So this quantity right here is negative 1, and this quantity right here is h over delta L. Now the sine of 180, this one was cosine. The sine of 180, the graph of sine looks like this, and this right here is 180. So the sine of 180 is 0. So really all we have to do is replace cosine of 180 minus theta with just negative 1 times h over delta L. So we'll get negative 171.5 newtons. Again, the 5 was not a sig fig times delta L times. Now I've already put the negative out in front, so now I just have the cosine of theta, and the cosine of theta was h over delta L. So you can see that I get exactly the same thing I did before because the delta L's cancel out, except the difference is now a negative sign. So we get a negative 2143.75 Newton meters, and 3 of those are not sig figs. Therefore, we can say the work done by gravity is equal to negative 2.14 times 10 to the third joules. Any questions on that one? Oops. No questions? All right, let me make sure I put my chatting screen up here. Ah, there it is. Looks like everybody's just been putting their name in for roll, so that's cool. I just want to make sure I hadn't missed any questions. Yes, that's cool. So, no questions on that? All right, well, let's stop a second and look at another problem. So, I'm going to go to sharing again. This time, I'm going to share my examples page. And that's the screen right here. And we're now doing example 2. It says, example 2, a force pulling a wagon has a magnitude of 25.0 newtons and makes an angle of positive 36.9 degrees with the horizontal. Excuse me. If the wagon is pulled horizontally a distance of 100.0 underbar meters, what will be the work done by the pulling force? Now, remember, when I write 100.0 with a bar under it, that's just me trying to tell you that 100 is 3 sig figs, and the underlined digit is in fact not a sig fig. So whenever I underline a digit, it generally, unless I tell you otherwise, it generally means that's not a significant digit. So now let me write down example 2. I'm just going to write down the data and then I'll share my iPad screen with you again. So this is example 2. What we have is a force that's doing the pulling that is 25.0 newtons, and the angle theta is positive 36.9 degrees, and the distance traveled D is 100.0 meters. So I've gotten the information I need. I'm going to go ahead and now stop sharing the screen that way and start sharing my iPad screen. Sorry for the back and forth, but got to do what I got to do. So now I can go ahead and draw you a diagram to make some sense of this. So what we're looking at is, you can imagine a box sitting on a level surface like this. And what you're going to imagine is happening is we're going to cause this box to move through a displacement vector d equals 100.0 meters. And we might say that's in the I hat direction, but since I don't have enough room to fit the I hat, I'm just going to call that the magnitude. And you see it's a horizontal vector. Now, we also have a force acting on this box, and that force is 25.0 newtons. And by saying it's a positive 36.9, we're assuming the x-axis points to the right, and we're going to go counterclockwise 36.9 degrees, like that. So hopefully by now you realize whenever someone says a 37 degree or a 36.9 degree angle that they're talking about the 3-4 triangle. If you don't, that's okay. You can just do the math and it works out fine. But we're going to go ahead and use that because what they're asking in this one is what is the work done by the pulling force? So the work done by the pulling force, I'll call it work FP, is going to be equal to F dot D. Okay. Well, we know our formula for the dot product. There's a couple of them actually. It was A dot B equals the product of the magnitudes of A and B times the cosine of the angle between them. But you could also figure it out from the individual components of the vectors, and it'd be AX BX plus AY BY. Notice this is a scalar. There's no I hats, J hats, or K hats in it. And AZBZ. So those are our formulas. Obviously, we could use either one, but there's one that looks really, really easy. Okay, so the one that looks really, really easy is the A dot B equals AB cosine theta. So I can put the magnitude of the force, which is 25.0 newtons, and I can multiply that by the magnitude of the D vector, which is 100.0 meters. And then all I have to do is take the cosine of the angle between them. Notice if I slid this D vector, if I slid it up, it would go right here. And then I'd see that the angle between them is in fact, when it's tail to tail, is in fact 36.9. So all I have to write is cosine 36.9 degrees. Now, of course, cosine 36.9 gives you the adjacent over hypotenuse, which you'd expect, and the 36.9 is the smaller angle in the 3-4-5 triangle, so that should be the one that would be opposite the bigger side, the smaller side, which would be the 3 side. So the bottom side, the side that it's actually touching, is the 4 side, and the hypotenuse was 5. But what do you have to multiply by 5 to get 25? It turns out you have to multiply by 5. So this triangle, instead of being a 3-4-5, becomes a 15-20-25. So the 15 is the vertical component. So you could say this is 15, and you could say that this is 20, and then of course this is 25. So really all I'm doing is multiplying 20 times 100, or you can just punch it in your calculator and see what you get. That's certainly fine, but I'm trying to show you how to make use of these special triangles. So 25.0 newtons times the cosine of 36.9 gives us very, very close to 20. 20 times 100 is 2,000. And that comes out in Newton meters. Notice I only had 3 sig figs for everything, so this 0 and this 0 are not sig figs. So now I can say the work done by the pulling force, actually I didn't write that very well, the work done by the pulling force is equal to 2.00 times 10 to the third joules. So there's an example again of using a dot product. Now, if you actually wanted to use the other formula for the dot product, I want to show you how to do that. So let me real quickly show you what that is. I think it's obvious that the d vector pretty much only has an x component if we assume that our x-axis is pointing to the right and our y-axis is pointing up, then the d vector only has an x component, and that x component is 100 meters. So 100.0 meters, and it points in the positive x direction, so that means we put an I hat by it. Now we could also say the pulling vector, which is f, let's just call it f or f sub p. Now, in that case, we already seen that it has a 20 Newton x component, so it's going to be 20.00 newtons, and that points in the positive I hat direction. Plus, we have a 15 Newton y component, so that's going to be 15.00 newtons in the j hat direction. So now you can actually dot product them by saying FP dotted with D is equal to FP sub X D sub X plus FP sub Y D sub Y plus FP sub Z D sub Z. As you can tell, we don't have a lot of those components, but we do have a X component of FP that's 20.00 newtons, and we have an X component of D that's 100.0 meters. We have a Y component of FP that is 15.00 newtons, but the Y component of D is 0, and then both the z components for both of the vectors is 0. So that's what the dot product is. And you can see immediately that we did in fact get the answer of 2.00 times 10 to the third joules, which is a good check. Anybody have any questions on that? Okay. Now, last time I actually used work equals, or excuse me, I used the definition or sort of a neat little theorem from vector calculus and mathematics in general that says that the change in potential energy, if such a potential energy function exists, is the negative of the work done by the conservative force. Of course, if the force is really conservative, then automatically it will have a potential energy function, a scalar potential energy function that fits this. So we did that, and what we found out was potential energy due to the gravitational force, at least while you're close to the surface of the Earth, is m times g times y, where y is your height over some arbitrary height that's close to the surface of the Earth. It doesn't matter what you consider the zero to be. It could be, for instance, the height of the ground directly below a roller coaster, and then it could also be y equals 0 at the lowest point on the roller coaster. Long as you stick with your definition of what y equals 0 is throughout the whole problem, you won't have any problems. You're always allowed to add any arbitrary constant to a potential energy function. So I'm going to go ahead now and show you a third example where we're now going to use a result from calculating the work done by stretching a spring. So before I start that example, let me show you what we call Hooke's law. So if you imagine a bit of wall by the corner, say, so this is the floor down below, and this is a vertical wall to the left. And what you can imagine is a spring that looks like this. Now, we use a spring in physics to talk about this specifically because if we tried to use just rods, like 2x4s and steel rods and stuff like that, or even toothpicks, uh, you'd have to put a pretty large force and then be able to use a really small measurement device to figure out exactly how much stretch a given force causes. But what Hooke said was F is equal to negative some constant times x, and this is called Hooke's law. I'm pretty confident there's an E in it, but all of a sudden that does not look good to me. So just check me if I'm wrong and correct it in your notes. But I could have sworn, yeah, I'm pretty confident it's Hooke, but that just looks funny when I wrote it. What this is saying is that you can treat the x as if the origin of the x-axis is right at the equilibrium position of the spring, and then the x-axis points in one direction for the positive x-axis, which I'll say to the right, and then this would be the y-axis up here, and this would be the origin. So if you actually pull on the spring, spring, if you pull on it to the right, then the x is going to be a positive value. So if you plug in the x in f equals negative kx, you get a negative k times x. And that's negative is showing you that Hooke's law says the force that the spring is going to put on you when you stretch it out to a positive x is in the negative direction. It's a restorative force. So that's why that negative's in there. If, on the other hand, you compress the spring, so you push it to the left a little bit by an amount x, well, then your amount x is actually a negative quantity. And if you put in the negative quantity for x, you get negative k times negative x, which equals positive kx. And that's the force that the spring is putting out. In this case, the spring is pushing to the right. Again, you compressed it by pushing to the left. The spring responded by pushing to the right. And in the first case, you stretched it by pulling to the right, and the spring responded by pulling back. So that's really what Hooke's law is trying to show you, and that's why the negative is in there. The K is something we call the spring constant. Okay, and it's just the spring constant really for a spring. Again, what Hooke said was this applies to all objects. So if you took a 2x4 and you found for this particular temperature the 2x4 was 8 foot long, if you then put it in a huge type of press that could try to compress that 2x4, you can already see the danger that's coming into that. If you started to do that, Hooke's law says that as you apply some big force F to it to squish it, it's going to shrink. Its x is going to change from the equilibrium length to a little bit smaller, and that change in length, that little bit smaller that it got, can be gotten from F equals kx, and that k is in this case not related to the spring constant. It's a property of the material. If I remember correctly, I think this one's Young's modulus. So you could look up that sort of thing. So that's what Hooke really said. But by using springs, we can use real small forces and get easily measurable changes in the length. So now that I have introduced that, I can go ahead and calculate the work done in stretching a spring. So let's say the work done in stretching a spring is equal to the integral of F dot dl. Because this is a varying force, just like the F equals mg could have been, but it wasn't specifically because the G, at least the ranges that we were talking about, were really small. If we go back to chapter 6, though, we would realize that G, lowercase g, is, let me write it right here. So lowercase g we found was G times the mass of the Earth divided by the radius of the Earth squared. So if you are talking about, and it's really the radius of the Earth, but that's only at the surface of the Earth. Really, the R in the bottom is the distance from the center of the Earth to the object. So if you stay close to the radius of the Earth, you would be on the surface of the Earth, and a height of 100 meters wouldn't even be a round off error. So that's why we could ignore it and just say mg was the force. But if we did it more uh, directly with this formula instead of the lowercase g being a constant, then we get a more accurate figure that would work for any distance from the center of the Earth. In this case, we're going to say work is equal to the integral of the force dotted with dl. This is a variable force, so we actually have to do the integral. And what I'm going to do is I'm going to imagine applying a force to this spring. Actually, I don't want that color. I think I'll take this color. I'm going to apply a force to the spring. And what's going to happen is the spring is going to stretch to a new position x. Let's call it x1 just to keep it different from the actual coordinate. So we're going to stretch that from x equals 0 to x1. The force we know is going to be k times x. And the dl is in the x direction, so that's just going to be dx. Everything here is moving in the positive direction, so you don't have to worry about that rule I told you about. You have to show the direction of integration with respect to dl by using the dl or by using the range of integration. In both cases, they're positive, so it's the same thing. So there's no danger in it here. What we know is the integral of kx is 1 half kx squared, so we end up getting 1 half k x squared, but then we evaluate it at x1, so we get x1 squared minus 1 half k 0 squared. So that's the work required to stretch a, or in that matter, you could also do the same calculation for compressing a spring and you get the same results. But that is the work done in stretching a spring from the equilibrium position to a distance x1. Okay. Now we can use this information to solve other problems. And in fact, you can even treat that as a potential energy function for the spring. So if you have a spring, there'll be a potential energy if it's motion up and down, for instance, gravity plays a role. Therefore, you would have an up and down potential energy associated with gravity. But if something's also compressing or stretching a spring, you'd have another potential energy that could be associated with 1 half kx squared. So now let's look at example 3. So I'm going to stop sharing for a second and start sharing the other screen again. And here's that other screen. And what we're looking at here is as a person pulls on a spring, stretching it 3.25 centimeters from its equilibrium position, which requires a force of 80 newtons. How much work does the person do? This is a very, very typical type spring problem. So what they gave us in part A was they gave us that the change in X, which I'll call delta X, is 3.25. I'm writing it down right now, but I'm going to share it with you in a second. So that's 3.25 centimeters. And the force that was required to do that was F is equal to 80.0 newtons. And what they want to know is what is the work done. And then in part B, they're saying, what about if you compress the spring? What would the work be done? So B, consider compressing rather than stretching. So that's really what the question is here. So now let me go ahead and stop sharing. Hopefully everybody's got example 3 there. Now that you have example 3, I can stop sharing and I can go back and share my iPad screen again. Share, share. Okay. So something might jump out at you. What we know, for instance, is we know that the work done in compressing a string, or in this case, we actually did it in stretching a spring. So the work done in stretching a spring is 1/2 k x squared. If you imagine doing this integral where you went from x equals 0 to x equals negative x1, you'd see that you get the same answer anyway. So we'll use that in part B. But right now for part A, we're going to make use of work being equal to 1/2 kx squared. We're also going to make use of F being 80 newtons. Oh, I already wrote that above, so there's no need to rewrite it again. But the force being 80 newtons and the corresponding stretch being 3.25 tells us that using Hooke's law, ignoring the negative because you really only care about the magnitude here, but ignoring the negative, F is equal to kx, which I'll say Hooke's law. Okay, and I put it in quotation marks because I didn't include the negative. So with this case, I'm going to write 80.0 newtons is equal to K, and I'm going to say X, which should really be in meters, so I'm going to call it point 0.0325 meters. So this is very typical of spring type problems. They'll give you some information in one line that tells you enough information to figure out what K is. It's usually when you apply this force, the string compresses this much, or when you apply this force, the string stretches this much. That's just a thing that allows you to get K, just like I just did. All I have to do now is solve for K. Then they'll ask you something like, what's the work done in here? And that's meaning, hey, we know that you have K now, so let's figure that out. So now I can go ahead and say that K is obviously going to be 80.0 newtons divided by 0.0325 meters. And you can see that the units for K are obviously newtons per meter. So I'm going to take 80 divided by, 80 divided by 0.0325 gives me 2,461. And I'm going to say zero point 0.5. That way I have two sig figs, and that's newtons, or two extra sig figs, and that's newtons over meters. So only the 2, 4, and the 6 are significant figures. But like I said, it's always best to carry a couple extra figures until you get to the very end. Now that I have that, I can just go ahead and calculate the work. The work done in stretching, which I'll call work ST, is just going to be equal to 1/2 times 2461.5 newtons per meter times, now the stretch was 0.0325 meters, and that has to be squared according to the formula. So I'm going to say zero point 0.5 times the answer I just calculated, which was K, times 0.0325 squared, and that gives me 1.3000. Notice the units are newtons times meters. And of course, we only have three sig figs, so these last two are not good. But that's actually it. So the work done in stretching the spring is 1.30 joules. Any questions on that one? Now for part B, they want to know what happens when you compress it. So again, work, well, let's write it in the same color I was using. Work done in compressing is equal to the work done in stretching, as I explained to you, at least in words earlier. So it's going to be 1/2 kx squared, and that tells us immediately that the work done in compressing is equal to 1.30 joules as well. Any questions on that one? All right. So that's another example, and we're almost just completely done with chapter seven. Chapter seven is really, really short. Remember, I think your homework's supposed to be due this Sunday or something like that for this chapter, and then we're going into chapter eight. But before I move on, now we've seen sort of all the different things you can do. We've learned how to use the work equals F dot delta D or F dot D or something like that. And that's in the case where the force is a constant, but not necessarily parallel to the delta D or to the delta or whatever. And we've learned how to use work equals integral of F dot DL with MGH, and we've learned how to do it with 1 half KX squared. So we know what to do when we're given a force formula to find out the work being done. But it might help for us to have one more example, and that's going to bring us to the next example I'm going to work, and this is going to be example 4. We actually had it written up there so you can always look at it because it showed up every time I showed the example. But I'm going to read it out and I might take the time in a second to show it to you. But right now I just want to keep on the fly. So what it says is a robot arm applies a force of magnitude f of x. So here's the example, and this is example 4. So we have a magnitude of the force, f of x, is given by this f0 times 1 plus 1/6 x squared over x0 squared. And we're told that f0 is actually equal to 3.0 newtons, and x0 is 0.00080 meters. Now we're going to calculate the work done in going from x1 to x2, and that implies x1 is 0.010 meters and x2 is 0.05, nope, 0.60 meters. So that's what we're looking for right here, is what is the work done by this force in basically moving an object from x1 to x2. So the way we work this is as follows. Solution.
Wait, what implied the position of x1 and x2 again?
That was part of the question. We had to give it to you. So that's a good time for me to go ahead and do the sharing that I said I could do later. So let me go ahead and do that real quick, just to make it a little bit more straightforward. Now, see this example 4. It says a robot arm applies a force magnitude given by the following. F of x equals F0, 1 plus 1/6 x squared over x0 squared, where F0 is 3 newtons, x0 is that. How much work is done in moving from x1 equal 0.010 meters to x2 equals 0.60 meters. Does that make sense now?
Yes, thank you.
No problem. So all we have to do with this one is obviously we're just moving it along the x direction. The dot product's not even relevant here because the vector is completely in the x direction, evidently. So we're don't have to worry about cosines. All we're doing is the integral of f times dx, where I'm integrating from x equals x1 to x equals x2. So work is equal to the integral of f dot dl. That's what we normally do, but in this case, everything's in the x direction. So I'm going to say the integral from x equals x1 to x2, like that. And the force is going to be F0 times 1 plus x squared over x0 squared times dx. So the F0 can completely come out in front. That's going to be F0 times the integral of 1 plus 1 over x0 squared times x squared dx. And I'm just writing that a little freer in hopes that the integral looks a little bit more reasonable. I'll go ahead and keep the symbols in here just so you can see what's happening, but then we'll plug all the numbers in the end because I hate plugging in numbers.
Could you show your iPad again if you don't mind?
Oh, yep, that would be helpful. Sorry. Sorry about that. All right, so I'm going to stop sharing now. Thanks for reminding me. I think that's funny every time it happens, but really it's clearly that I'm becoming a moron. Here we go. Here we go. All right. So notice what I wrote here. We had the f.dl, but like I said, this is a f sub x, so it really is supposed to be like an x component of force. So it's already been made to be parallel to the displacement that you're making, which is obviously along the x-axis. So the dot product becomes nothing. So all I have to do is really take the force and multiply it by d parallel to the x-axis. But d parallel to the x-axis is just dx. So that's what I'm doing here. I took this f0, which is a constant, and put it out in front. And I took this, which is another constant that's being multiplied by x squared, and put that out in front. So it might look a little less distracting when you go to integrate it. So I'm going to carry on with my integration. Does that make sense to everyone? I know I didn't give you much time to write it down, and I'm going to let you do that now. But make sure everybody follows it before I move on. All right, it does not appear that we have any questions, so I'm going to continue. So the f0 is still out in front, but the integral of just 1 times dx is just x. So we know already that this is going to be x2 minus x1. So that's what we get from taking the integral of just 1. The integral of 1 is x, and then we have to evaluate it at x2 minus evaluating it at x1. That's why I got the x2 minus x1. Now we've also got to remember that I got 1 over x0 squared as another constant to multiply by the variable. This time it's the integral of x squared dx. And the integral of x squared dx is, ooh, I lost a sixth in here too. Everybody remember this had a 6 in it? Well, I forgot to do that. So there it is now. And let's do it. I could just guess I can just put the 6 down here. That'll be good. All right. So now the integral of, oops, the integral of x squared is 1/3 x cubed. So what I'm going to do here is put a parenthesis and then 1/3. And then remember it's now x cubed. So this is going to become x2 cubed minus x1 cubed. So we now got a lot of nested parentheses, but that's not terrible. We can go ahead and calculate that. So now I can put in the numbers. The f0, remember, is 3.0. And then that's multiplied by a square bracket. And in this case, it's x2 minus x1. So it's 0.060 meters minus 0.010 meters. And now you can see why I said 5 earlier, because when you subtract them, you get 0.005. Now we also have, in this case, I'm going to go ahead and distribute the 1/3 and the 1/6 to make it 1 over 18. And I'm also going to go ahead and plug in what the x0 is. So what I'm going to have is 1 over 18. Oops. 1 over 6 times 3 is 18. And then the x0 was 0.00080 meters squared. So that's all just in the denominator. So see, it's 3 zeros followed by an 80, and all that'll be squared. Now all I have left is the cube of these values. So it's going to be 0.060 meters cubed minus 0.010 meters cubed. And that's going to have that and a square bracket after it. So now I can calculate all this junk. Again, this is 3.0 newtons. This is going to be 0.050 meters. Let's say 1. I'm going to try to compute that weird fraction out in front. So it's 1 divided by parentheses 18 times 0.0008. And now that quantity is going to be squared. And what that gives me is a really huge number. It becomes 86,806. And obviously, that's way more sig figs than we really had. So I am going to underline these three digits and notice it's meters to the negative 2 power. That's what that constant is right here. Okay. So now I'm going to take the point zero 0.06 and I'm going to cube that. And then I'm going to subtract from it the point zero 0.01 and I'm going to cube that. And when I do that, my answer is 0.000215, and obviously that gives me meters cubed. So now I'm in the position where I can do a lot of stuff. I need to take this 0.00215 and multiply it by the 86806, and that'll give me this last part. So when I multiplied 0.00215 by 86806, notice the units are going to work out to just be meters, but the answer that I get from that multiplication is 18.663. That's way more sig figs than is really reasonable, of course. In fact, we should only be having uh, 0.06 cubed. Oops. Oh, that's terrible. 0.06. I'm trying to make some sense of where this would be. So when I did the 0.06 cubed, I got 0.000216. So that's only good to the fourth and third decimal place. And then when I did 0.01 cubed, okay, I got the 1 in the sixth decimal place. So, to be honest with you, technically, even the subtraction was not supposed to be there. So the 5 is definitely not a sig fig, but the 2 and the 1 are. The 2 and the 1 times the 2 sig figs from the 18 times the 0.00080 is also okay. So yeah, it should be just 2 sig figs in there. I'm going to underline these three digits. But the ultimate result, of course, is just meters. So now I'll take that 18.663 meters and I'm going to add to it the 0.050 meters, and that's going to give me, oops, that's going to give me 3.0 newtons times 18.713, because I just added 5 to it, so that makes sense. And this is a meter, so the whole units work out to be, this times 3 gives me a Newton meter, and therefore I get that the work is equal to 56.14 Newton meters, or work is equal to 56 joules. Any question on that one? Okay. Does it like, hopefully it looks like everybody has chatted me your first and last name. Just wanted to remind you of that in case anybody came in late. There was one person came in late, but I'm not sure if they had come in before that too. So now we've done the four examples that I had planned to get done. This is completely finishing chapter 7. So now what we want to do is go ahead into, oh yeah, good, I got somebody. Now what I want to do is go ahead and start chapter 8. So here we go, chapter 8. Now, chapter 7 is necessary for us to even do chapter 8, but really all of it was somewhat just to get us prepared to do chapter 8. So what we're doing in this chapter is we're now applying the idea of conservation of energy. So we're going to use a method other than Newton's laws of motion and kinematic equations. We're going to use a different method that doesn't necessarily use those, and from it we're able to solve problems without vectors, and that's going to be conservation of energy. The chapter, as I said, is chapter 8, but it's called conservation of energy. So I already mentioned the conservative forces. So whenever you find a conservative force, then that means you can represent that force with a scalar potential, as we did with the gravitational force earlier, as we did with one half, or with the F equals negative kx force earlier, and as we did with we could do with the big gravitational force, GMM over r squared. We can do that as well. But what we're going to do is ultimately look along the lines of this. When I say conservation of energy, I'm meaning it's like a zero sum game. So, for instance, I usually explain it as, imagine TCC has 100 employees. And let's imagine that as TCC has only 100 employees, their let's say the money they have set aside to pay their payroll or their payroll specifically, is only $100,000. Okay. Now, if they tried to do sort of a communist type thing where everybody's 100% equal, or what was that? There was an old fictional story that we learned in grade school, Walter Mitty or something like that. And, or maybe it was yeah, it might have been the other one where they basically tried to make everybody equal, and they hung weights on each other and all this kind of stuff. Well, if you imagine that, then each of us would be making exactly $1,000 because the payroll was 100,000. We had 100 employees, and they're all making the same thing. So that means each of us are going to get $1,000 per year. Now, we're not really paid that badly, but the numbers work out nice, or nicely, excuse me. So since we have that, when I'm talking about a zero sum game, now imagine that we have 100 employees, each making $1,000 a year, and I get cocky and I walk over to the dean's house or office and say, "Hey, I'm Mr. Younger. I do this, 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 and this, and I have these great evaluations. I think I'm worth a way more than the rest of the people here." And this guy, this man or woman who happens to be my dean or whatever person I go to, assuming they really bow that, which obviously they wouldn't, and I'd say, okay, well, I'm going to accept now $4,000 per year. And he says, okay, well, we got to keep you. So, yeah, you made a really good point. So now what we have is still a $100,000 budget, but we now have 96,000 of it to pay 99 employees. And because of that, now I'm making 400 or $4,000 a year, and the rest of the faculty is only making $969 and 69 cents. That's what I mean by conservation law, or a zero sum game. Anytime you're thinking in terms of anything that that person gets positive makes a negative on me, or anything that that person does negative makes a positive on me, that's what we call a zero sum game. Just in case you're wondering what those words I'm saying, it's zero sum. I learned that a lot of times students don't understand the words we're saying because they never read them. They see them, or see them. They only hear them. So, for instance, I once noticed a person had written a note about taking her for granted, which is what you're supposed to say, and she actually wrote granite. Now that happened to be a female. I'm not saying that anything bad about females. Obviously, I could find a male that would do the same thing. But the big thing is, I would like you guys to sometimes see the words that I'm talking about. So now that we have that, you have some understanding of conservation of energy. What I like to tell my students is you can sort of imagine that the total energy is in a Ziploc bag. So if you draw a little Ziploc bag like this, and it's one of the fancy ones with the yellow and blue make green seal, right? So you know it's 100% not going to leak. That's the total amount of energy that you have in a system. But you could break that up into little permeable membranes separating certain baffles, and this might be gravitational potential energy. And then over here in this other baffle, now the baffle just means you're sort of keeping it separate, but you can make it flow through that little wall back and forth if you need to. So we're also going to have a potential energy that's due to a spring. And then we're also going to have kinetic energy, K. Okay. Later, you'll discover that there's another form of kinetic energy as well, and that's K rotational. So you can imagine all the different types of energies that you wanted, and what the total energy is all the sort of air or whatever in that Ziploc bag. And for instance, if I wanted to imagine what would happen if I stopped all the motion, then all the kinetic energies would go to zero. So I could squeeze those right two baffles. I'd squeeze them completely flat. And when I did so, the UG and the baffle would get really, really full. But the total amount of air inside is still the same. So that's what we mean by conservation of energy. So the way we implement this in terms of physics is we normally do some, or most people do something like this, and it's delta U plus delta K is equal to zero. That's a very typical way of doing it. And you just have to remember that delta implies uh, final minus initial. Okay, whenever you have a delta with something after it, it means that something final minus that something initial. So, for instance, delta U would equal U final minus U initial. So if you ever see a delta, and this includes in your chemistry, your physics, and your engineering classes, if you ever see a delta, they have to explicitly tell you that this is not final minus initial if they're using it. Otherwise, you can go on the assumption that the delta means final minus initial. So now that we have that, that's one way of actually solving physics problems. So for instance, you could imagine that at some height, let's say this is our x-axis, this is our y-axis. Let's say this height right here is 3 meters above the ground, and I launch a ball upward with a velocity v equals 5, no, let's say 19.6 meters per second. And let's say the mass is 1 kilogram. And we can say that 3 meters is 3.00 if we want it. Now, what we know is that delta U plus delta K is equal to zero. So we might want to find out, well, how high does it go? Well, all we have to do is say U final, which would be M times G times Y final, minus M times G times zero. Notice I drew it right on the x-axis. Even though that's 3 meters above the ground, I'm allowed to put the zero anywhere I want. I chose to put the zero 3 meters above the ground. So that's U final minus U initial is MG final minus MG zero. Okay. Now, what we also had was the final kinetic energy. If the ball reaches its max height, that means it has zero velocity at that time. So the final kinetic energy would be 1/2 times m times zero squared minus the original, which is 1/2 mv initial squared. And all that has to equal zero. So now I can say 1.00 kilograms times 9.80 meters per second every second times y final uh, minus 0 plus 1 half 1.00 kilograms times 0 squared minus 1 half 1.00 kilograms. And then the V initial we said was 19.6 meters per second. Now we're going to square that and everything's equal to 0. Okay, you can already see, of course, that that 0 and that 0, so we didn't really need those. I just was being complete. Now what I can do is I can take the zero point 0.5 times 19.6 times 1 times 19.6 again, and that gives me 192.08. It would be negative as it's written, but I'm going to pull it on the other side, and that gives me 192.08 joules is the amount of kinetic energy, and that's equal to 9.80 newtons times Y final. So Y final turns out to be 192.08 divided by 9.80, and I get 19.6 meters. That really is surprising to me. But anyways, we have that. Now, if you looked at this in terms of the symbols instead of the numbers, watch what happens and we'll be done. If you need to leave, go ahead. I'm just wanting to show, close the loop on this. So you guys are free to go. Make sure you chatted your first and last name if you haven't already. But I'm going to finish this out. Might take me 2 minutes. So what we really had was M times G times Y final. That was the final potential energy minus 0 plus 1 half mv final squared minus, which remember that was 0 as well. In fact, I could, well, I'll go ahead and leave it with a 0 here, but I could have went ahead and made that term a 0, but I'm choosing not to for a reason you'll see in a second. And now I have 1 half mv initial squared. All that's equal to 0. What you see immediately is that there's a common factor of mass that can be canceled out all the way through that. Now, if you want to solve for, let's say we want to solve for V final. Watch what happens. What you end up getting is V final squared is equal to V initial squared plus 2 times G times Y final. Does that look familiar to you guys?
Looks almost like a kinematic equation.
It is exactly the kinematic equation. So that's sort of the neat point I was trying to make for you. Obviously, what you mean, you're right. It's a G in there instead of A, the generic phrase for the acceleration. But in this case, the G happened to be the acceleration. But yeah, that's just one of the neat things that I've now shown you a method that we can use to figure out, for instance, the max height or the final speed or something like that without using kinematic equations and without using vectors, yet I still managed to get exactly the kinematic result. So that's sort of just a quick little neat thing I wanted to show you about conservation of energy. We'll jump in using this. I actually use a different system, and I'll show you that next time. But right now, you can certainly start the homeworks, but make sure you knock out Chapter 7. You should be done there. Make sure you guys finish your online test. That's due this, I think it's due this weekend, Saturday, I believe, or Sunday, I believe. So make sure you get that and any homework you have done, have to get done. Make sure you get those done. Y'all have a great weekend. Stay safe, and feel free to send me a text or an email if you need anything throughout the week or weekend. Thanks, everybody. I'll wait till the last person leaves in case anyone needs to ask me questions. Aiden, you there this time, bud? All right, I'm going to go ahead and stop sharing. And I don't think Aiden is actually there anymore. Oh, yep, he's gone. All right, so have a good one, everybody. Bye bye.